Now let's talk about error backpropagation, which is the algorithm that we can use to train multilayer perceptron. So the point then with the neural network that we saw so far, which is the basic model of a multilayer perceptron, is to determine the weights W and W0 for all neurons. So we see so far that with different topologies, we can achieve different results. We see that it is able to make it is an interesting model that make a nice approximation, that has good capacity to fit any kind of data that is inspired by the brain of human and animals. But the big question is, how can we learn, how can we determine the good weights to use in our model? So we are making use of what we call error backpropagation, which was first proposed in 1985 by several persons. This is based on gradient descent. And this is really the first well-known approach that was allowing to train neural networks that was not basically one layer neural networks. So it was allowing to learn nonlinear modeling through neural organization and a neural network. So the learning in backpropagation is done through gradient descent, as we saw before with linear discriminants. The point is that we are looking first at the output layer, and that output layer is providing us some output, some decisions on a given data. We can compare this with the desired output, and computing the difference is giving us an error that we use to guide the learning. So that error between the obtained output and the desired output is giving us an error, and this error is used through gradient descent to adjust the weights of first the output layer, and then we go inside the network. So going from the output, we go with the hidden layer just before the output. We adjust its weights according to the sensitivity, so the influence of the neurons on that hidden layer with the output that we observe at the output layer, and we make some adjustment of the weights and so on from the output through the network up to the input. So we are backpropagating the error in the network. So the model looks like this. So basically here we see the output layer. That output layer has some error that we compute, with EIT and EKT are basically the error that we observe between the desired output and the obtained output. And then we have all these factors here that is giving us the sensitivity to correct, to adjust the weights. And so they are passed through, and we are using them to adjust these weights, for example, which is then used to evaluate the new sensitivity for neurons that are at the hidden layer, since the one just before the output layer. So that sensitivity is based on all of this. So it is based on all the individual sensitivity plus the weights that we have that is connected this neuron with the one on the output layer. And we are also connecting this with to compute the sensitivity of the neurons before the current neuron on the hidden layer, and so on. So we are kind of backpropagating the signal. So we are going from the output here, we are backpropagating the signal through the network up to the input. And this is done by gradient descent. So let's first look at the value of the neuron J for the data xt. So we are looking at some value of the neuron. So here we have YJT, which is the output of the neuron J for the input data xt. But this data input xt is not directly available. In fact, what we have as input is the output of the neurons at the layers just before the current layer. And so, and this is computing from the output from the neurons layers before the last layer, and so on until the input. So F here is the neuron activation function, which we saw before. Just when we start with the modeling of a neuron in a neural network, we say that we have a transfer function and activation function. And A here is basically that thing. So it's basically the linear modeling where we are making a weighted sum of the input of our model, which is the output of the previous layers, multiplied by a weight plus some bias. So we can see this thing here, the weight, the inputs, and the bias, which is giving us the A value, which is the value before that is given to the activation function. And then we have the weight WJI, which is connecting neuron J on the current layer with neuron I from the previous layer. Then we have the bias WJ0, which is the bias of the current layer, the current neuron J. And the YIT is the output of the neuron I on the previous layer for the given data XT. And we have R neurons on the previous layer, which is depending on the neuron each time. So if we are looking at the output layer error, so we say that we have a data set. So this is our data set. We have some the target labels. So basically, we have RT for K classes, for example. And we see here that this is a one-hot vector in the sense that RJT is equal to 1 xt from the class CJ. So we set a 1 in the vector for the RT coming associated to the class of XT. And the other RT, RJT are equal to 0. So otherwise it is 0. So for example, if we're dealing with 3 classes and we say our data is coming from the second class, we will have a vector of 0, 1, 0. That means that we have an instance that is coming from class 2, and because this is R2, T is equal to 1, and the other R's are equal to 0 because it is not coming from C1 nor C3. And so we are observing some error for a given data XT on the neuron J for the output layer. So we are at the output, so we directly compare our output, which is YJT here, with the desired output, which is basically the RJT corresponding to the vector that we define here. And so this difference is giving us EJT, which is the error measurement for that neuron for that data instance. And then we are evaluating the quadratic error. So this is the error observed over all the output neurons. So we have, it says we have K classes, we have K outputs, K neurons. And as such, we are computing the quadratic error as the sum of the square of the individual errors on each neuron. So we are summing this from neuron 1 to neuron K on the output. So basically output 1 to K. And well, 1/2 of that, just to simplify the equation. This is giving us the quadratic error observed for XT. So this is the error for one data instance, which is the XT. And then we can evaluate the mean squared error. So the difference is that we are making an average over all data from our data set. So we have this data set here that has n samples. So we are summing over the n samples, the quadratic error observed for one sample, for each sample. So we are summing this quadratic error, and that is giving us the mean squared error here. And then we need to evaluate the correction to make for each weight. So this is done through gradient descent. So we are starting from the mean squared error that we just defined, and we say, okay, the delta to apply, so the correction to make to the weight WJI, which is linking current neuron, output neuron J with the neuron I from the previous layer. And as such, we are evaluating then the correction applied to the weight through gradient descent, so minus eta. So we are descending the gradient, the gradient with a learning rate of eta, and we are computing the partial derivative of the error, the mean squared error for that parameter. And as such, if we expand the equation, is basically to compute this by summing the gradient, the partial derivative for each sample, going back to the mean squared error formulation. So this is it directly. So error of the neuron J depends on the neurons of the previous layer. So we need to connect this error with the output of the neurons of the previous layers, which are basically the input of our neuron J. And for developing this, we need to make use of the derivative chain rule, which is basically stating us that if we are looking for example, the partial derivative of f according to x, and maybe we don't have a formulation of f as function of x, but if we have f as a function of y and y as a function of x, we can apply the chain rule here, which give us that the partial derivative of f according to x is equal to df over dy times dy over dx. And so we are applying this, but with developing over 4 elements. So we have our partial derivative here, that is the partial derivative of the error for sample t according to the weight wji, which is the weight that we want to update. And that is developed as this thing. So we are looking at the partial derivative of the error, squared error for that sample versus the absolute difference between the desired output and the obtained output, the small e gt. So, and then we are using the derivative of small e gt over the output of the neuron J for the sample t. And then we are looking at the derivative of the output of that neuron after, so when we apply the activation function, versus a gt, which is the value before the activation function, so the input of function f. And then we are looking at AGT, which is basically the linear model that we have in a neuron. So we are looking at the partial derivative of AGT versus WJI. So we are kind of developing this. This is corresponding to the flow that we have in our model. So, we have the squared error for all outputs. Then we assign, so this is the first thing here. We are looking at this according to the error of neuron J. Then we are looking at the link between the error of output of neuron J versus the output of neuron J. Then we are looking at the link between the output of neuron J versus the value before the activation, which is called AGT, which is the output of the linear model inside it. And then we are linking the linear model with the weight WJI, which is the one that we really want to look at to get the partial derivative, because we want to adjust, in fact, the weight WJI. And as for the bias, WJ0, it's pretty similar, with the difference that we are making the last derivative according to J0, not Ji. Now we are developing this we are developing the partial derivative. So as such, we have making the developments for the sigmoid activation function, which is the classical activation function used with multilayer perceptron. So we have YJT, which is equivalent to 1/1 plus exponential minus AGT. So this is our sigmoid function. At first, we are looking for the partial derivative of the squared error for that sample versus the specific error for that neuron. So we need to compute the partial derivative according to the small e gt, given this is corresponding to AT, basically. And as such, the partial derivative of that gives us directly EGT. So we are able to get this partial derivative equivalent to small EGT. Then we are looking at the partial derivative of EGT versus YGT. So we remember that this thing is equal to that directly, and the partial derivative according to YGT is simply -1. Then we have a more fancy one. We are looking at the partial derivative of YGT versus AGT. So remember that we are using the sigmoid activation function. So this is what we are using here. So if we are computing the partial derivative of that equation according to AGT, we get into that thing. But this is not super convenient. We can simplify this even more. So we can get that thing. So basically we are expanding this by separating, this part, which is basically what we have here. But one of the one times here, but the second one is there. So we have 1 plus exponential minus AGT square here, which is developed into these two sides. And we are doing this because this thing is basically YGT. So this is it. And that thing, if we are just managing this, is equivalent to 1 minus YGT. Remember, we saw this in the presentation on linear discriminant. This expansion has been done first for logistic regression. So we are using the same developments that we had with logistic regression to simplify this partial derivative as basically something expressed in terms of YGT. So this is coming from the use of sigmoid activation function. And the last partial derivative that we are looking for is the one of alpha G of AGT versus WGI. So remember that this thing is simply the linear model that we had. In fact, it is the whole thing here that we had before. So the point is that, we are making a sum over from 1 to R, which R is the number of neurons on the layer before the current layer. And as such, if we go from 1 to R, all these different WJL are not useful except in the case where L is equal to I. So this is only in that case where we have WJI. So this is the case that we care. And so in that case, we have the derivative of WJI YIT. And this is equal to WIT directly. All other cases in the summation are equal to 0 because there are no presence of WJI except for the L equal to I. And finally, we have the same derivative, but according to WJ0. So then it's basically the derivative of WG0 according to itself. So it's 1. And from that, we are defining the learning from the output layer weights. So we have a delta, so the modification to apply to weight WJI is equivalent to minus eta over n. So this is basically for the mean squared error of the whole training set. And we develop this as that thing, but now we have computed every of the partial derivatives that we have here. So it boils down to that thing. So basically it's eta over n summation for all samples of the observed error between the output and the desired output for that sample T over that neuron J. The output of neuron J, 1 time the output of neuron J. Sorry about that. This thing is for the output of neuron J. This is for the error between the desired output of the obtained output. And down here we have YIT, which is the output of neuron I on the previous layer. In fact, this is according to the weight WGI. Remember, WGI is the connection between neuron I from the previous layer to neuron J of the current layer. So we need to look at the output of that neuron on the previous layers that is passing through the link that is weighted according to WGI, and then going inside the neuron that is accumulated with all the other inputs and then fed as output, over which we compute the error. And as for the biases, so the WG0, which are basically the bias given to the neuron without any other connection with other neurons, it's the same development with the difference that we don't have WIT, we just stop at EGT. YGT times 1 minus YGT, this sum over all samples with the learning rate and divided by the size of the training set. So these are the update rules to use for training with gradient descent our output layer.